Okay, so now that we've talked about Pythagorean theorem and dilation, we're moving on to similarity. So the warm-up for you guys is to, right here, dilate the triangle. So we're going to use each corner of the triangle, and we're dilating it by a factor of 1/2. And we're using the origin as our center of dilation, okay? So if we look here, we have our triangle. We have a point here on this corner. It just said to use the corners. And my center of dilation is the origin. Where's the origin again? Right here, where the x and the y meet. Okay, it's the x-axis. So I am dilating by 1/2. So that means all my distances are changing by 1/2. So let's start over here. Over here, my graph is 3 over 1 up from the origin. So 3 times 1/2, okay? We can type that in our calculators. That's just 1.5. So we now move to about right here. And then 1 times 1/2 is just 1/2. So our next point is right there in the middle. Let's go over here. I'm 3 high, which means 3 times 1/2, we just said it was 1.5. So my new point, let's erase this so I can see my point nicely, is right here in the middle. We're timesing our distance by 1/2. Let's do this last one. Okay, I have a distance of 2. I'm timesing 2 by 1/2, which is just 1. So instead, that point should be half, should be 1. And 1 times 1/2, right, because we're just going up 1 square, that's 1/2. So my new point is right there. So let's erase these so that you can see this a little bit nicer, and I'll connect the dots. So this is my new triangle. Again, did the shape change? No, it stayed the same. It just shrunk, okay? And got moved a little closer to our center of origin. So remember, all we're doing is timesing our distances by whatever factor, okay? So now that we talked about dilation, dilation moves perfectly into similarity. So what is similarity? Well, we just said that these two triangles are the same shape. So we actually call these similar triangles. Okay? They're the same shape, just one was scaled down. It was shrunk by a factor of 1/2. Okay? And that's what similar triangles are. So we say two objects are similar if they have the same shape so the same shape, okay, and one can be obtained from the other by dilating. Or we can also call it scaling. So that's just timesing all the distances by a value, okay? So let me zoom out so you can see it. So two objects are similar if they have the same shape, and one can be obtained from the other by dilating or scaling. So, like those two triangles, one was just shrunk. It was scaled down by 1/2. Same shape, but every single side length was the same. So let's kind of look at question 2 here. Dilate the triangle by a factor of 2. And it says to use the origin as the center of dilation. So here's my point, here's my point, here's my point, and the origin, which is right here, is my center of dilation. So how far is this one? Well, it's 2 over and 1 up. And we're dilating it by a factor of 2. So we have to times our distances by 2. So 2 times 2 is 4, so it's going to be over here. 1 times 2 is 2, so our new point is all the way up there. This one, it's down 2, so it's now going to be down 4. The next one, over 3 up 2, it's now going to be over 6 up 4. Okay, so connecting our dots. Okay, so if we measure all the side lengths of the triangle, I'm not going to make us do this with a ruler and try to measure it so we can see that they're the same, but really this distance right here is just going to be 2 times that distance because we times everything by 2. This right here is going to be 2 times bigger. And this long distance right here is going to be 2 times bigger than that distance. Every single one of the side lengths was also multiplied by 2. We stretched it by a factor of 2. So are these triangles similar? Yes, they're similar. Okay, so let's kind of practice looking to see if these triangles are similar or not. Let's look here. So I have a side length of 180, a side length of 100, and a side length of 140. Then I have another triangle that looks like this one that has a side length of 90, side length of 50, and a side length of 70. Well, what's the difference between 180 and 90? Well, we can even type that in our calculator. What's 180 divided by 90? If we type that in our calculator, what do we get? We get 2. Okay, so the difference between these two is 2. What about here? If I have 100 divided by 50, what do I get? I get a difference of 2. This 100 is twice as big as a 50. Okay, what about this 140 and 70? So 140 divided by 70, we get 2 again. It's twice as big. So each side length is twice as big. So are these triangles similar? Yes, they are similar. Because every side length is twice as big. We stretched every single side length by 2. Let's look over here at question 4. Okay, so the matching sides, I have 141 and 197. I have 100 and 170. And I have 100 and 100. Well, let's see this for a second. 141 divided by 197. What does that give us? I got to type that in my calculator because I don't know. 141 divided by 197. That gives us about 0.72. Let's try the next one. 100 divided by 170. That gives us about 0.59. And then the easy one, 100 divided by 100, that just gives us 1. Are these factors all the same? No, we didn't times the distances. This distance, or how much this one's bigger than the other is by 0.72. Okay, that's the difference. All the differences are different, so we didn't scale, we didn't stretch the side lengths the same. So no, they are not similar. That factor that we're dilating from has to be the same on every single side length. And it's not. They're all different factors. So it's not similar, okay? So that's how we can tell. If we just look at the difference between the two on every side length, we can see that the factors are not the same. Okay, let's go to question 5. What do you notice about the angles on the triangles that are similar versus the ones that are not? So if we looked at this triangle, they're similar. What do you notice about the angles? Well, this had an angle of 32. This had an angle of 32. This was 100. This was 100. This one was 48, and this was 48. They're exactly the same. Okay, what about the one that's not similar? This was 45. This was 60. This was 30. This was 45. These were both 90. Are the angles the same? No. Okay, so what did we notice? We noticed that on the similar triangles, the angles are the same. They are not the same on the non-similar triangles. So on the non-similar triangles. So what does that mean? It means similar triangles have the same angles, okay? So that's what that means. Similar triangles have the same angles, okay? So, not only can we look at shapes, we can also look at ratios. So an example of ratios are recipes. And we can check to see if things are similar with recipes based on if we multiply and have a factor that is the same for every single one of these. So let's take a look at this sugar cookie recipe. So it says it has 5 cups of flour, 2 teaspoons of baking soda, 4 teaspoons of cream of tartar, 1 teaspoon of salt, 2 cups of sugar, 2 cups of margarine, 4 eggs, and 1 teaspoon of vanilla. So let's compare and see if this side of the recipe is the same or if they're similar, okay? So what's the difference here between 5 and 3 3/4? Oh, cancel. Okay. Let's see. What are we going to have to times by? So we can just type in our calculators. We can take 5 and we can divide it by 3 3/4. Do we know what 3 3/4 are? It might be easier if you think in decimal form. That's just 3.75, okay? So we'll go 5 divided by 3.75. We get a factor of 4/3. Okay, what about when we do 2 teaspoons divided by 2.5? Let's type that into our calculator.